Marvell just paid $3.25 billion for photonic interconnects. IR Labs raised $500 million betting on optics at a multi-unicorn valuation, and everyone in AI infrastructure seems to agree copper is dead. Srujan Linga, CEO of Kandou AI, disagrees, and he's just raised $225 million to prove it. Kandou is making the contrarian bet that copper still has plenty of room to run, and that the real bottleneck in AI isn't just compute, it's how fast you move data in and out of memory. And the industry chasing optics is directionally correct, but economically and contextually, copper still has a long-term play. So this week, Srujan joins us on Tech Threads to discuss the memory wall, copper versus optics fight or partnership, and why one of Silicon Valley's most unusual CEOs, he's ex-MIT, he's ex-Goldman Sachs, he's ex-CHIPS Act, is betting against that consensus.
Welcome to Tech Threads, Weaving the Intelligent Future, the podcast exploring the fast-paced world of technology. In each episode, we dive into the latest innovations in data movement, AI acceleration, and the transformative potential of chiplet technology. Join us as we explore the breakthroughs that shape the future of computing and hear from industry experts on what's coming next in the tech landscape.
Hello, and welcome to the latest episode of our Tech Threads podcast. I'm Nandan Nayampally, Chief Commercial Officer here at Biosystems. And if you've been tracking the AI infrastructure arms race, you've heard the phrase memory wall thrown around a lot. You've seen memory component stocks going up like crazy over the last few months. And in our June episode, we addressed the problem of the memory wall from the 3D memory perspective with TC Labs. Biosystems, of course, as you know, has been working on the data movement portion, and we're seeing a great deal of innovation of companies, technologists trying to break through the memory wall. So today, I'm talking to Srujan Linga, the CEO and co-founder of Kandou AI. It's a company he helped create from Kandou, which is a Swiss fabless semiconductor company that's been doing foundational work on chip-to-chip interconnect for over a decade, and now is a company that's geared towards solving fundamental AI infrastructure problems. They just closed a $225 million Series A, backed by SoftBank, Synopsys, Cadence, Allchip, and Maverick Silicon. Now, Kandou AI is betting on the fact that copper, the material that industry has been writing off in favor of optics, still has enormous untapped potential to scale, and more importantly, is proven, efficient, and cost-effective. Now, our guest, Srujan himself, has a fascinating background. So before transforming Kandou AI, he was a MIT electrical engineer, 16 years as managing director at Goldman Sachs, and then director of financial structuring of the US government's $53 billion Chips for America program, where he was also driving the AI task force at the Department of Commerce. So he sits at an unusual intersection, very deep tech credibility, financial markets and capital fluency, and of course, policy experience for industry and government. So this conversation is going to be interesting. It's about AI system design. It's about the whole industry. It's about who's too hung up on optics or not, and to see innovation come from more conventional materials. And I have to add this, Bio is proud to be a partner in their quest as a licensor of their fabric. Srujan, welcome to Tech Threads.
Thank you, Nandan. Thank you for having me here. And very excited about our partnership with Biosystems. You guys have a great team and really proud of what we've been able to work together on so far.
Yeah, thanks, Srujan. And in fact, we started working with Kandou even before it was Kandou AI. And it's been great to kind of see the collaboration, camaraderie continue. And I think the mission that you've set and the new team that has developed is really exciting to work with. So with that, right, I'll say, let's start with first principles, because, every time we have new listeners and some of them are learning it for the first time, let's make sure that we understand what we mean by the memory wall. Obviously, we talk GPUs, we talk compute scaling, But can you explain to us why the bottleneck today isn't just about chips doing math and math functions? It's about how it moves data to and from chip.
Yeah, absolutely. And then to understand that, we need to actually take a step back and think about how AI models work from a fundamental standpoint. And so when you think about, let's just take the latest AI model, frontier model, ChatGPT 4. It is a 1.8 trillion parameter model. And even if you assume 1 byte per parameter in terms of granularity, that's about 1.8 terabytes of memory that is required just to store the model. Number two is when you make an inference query on this model, there are about roughly 280 billion active parameters that are activated per token. And again, at 1 byte per parameter granularity, you're talking about 280 gigabytes of data that need to be accessed for every token that is generated. And so even if you were to create a 20 token sentence, that's about not close to 6 terabytes of memory that needs to be moved from your compute from your memory layer to the compute layer. And that is just for a 20 token sentence, right? So now you multiply this by hundreds of millions of users using AI models at the same time. And on top of this, you activate what is now the agentic AI phenomena, where the context frames are exploding, the context windows are exploding. And so this memory access, memory capacity, and memory movement problem is becoming increasingly the key bottleneck of how you build efficient AI systems, because we are no longer compute limited. It's all about how you efficiently move the data from your memory layer to the compute layer and back and forth, right? Just to give you a sense of how critical this problem is, what do you think? The people in the industry track something called the task horizon, which is the amount of time that an agentic AI model can spend without human intervention. That number was about five minutes about a year ago. Today, Nandan, take a guess what that number is. You have to unmute yourself, Nandan.
Yeah. Fair question. So I'm going to probably go the wrong way. Is it an hour?
Actually,
it's probably seconds.
You're not too far, actually. It's about 4 to 5 hours. So and that is doubling at a rate of a rate of 2x every 6 months. So basically, by the time 2027 shows up, you will be able to work a full work day with agentic AI models without getting interrupted, right? So what this means is that increasingly your context windows are blowing up, your KV cache is blowing up, and therefore this data movement problem and memory capacity problem is increasingly going to be the bottleneck. So this is what people in the industry refer to when they say it's a memory wall issue, because it's not just about your compute layer anymore for AGI, and our quest towards AGI and ASI is increasingly determined by how efficiently you move data from memory to compute so that you could actually process queries and train models quicker. And so we are very excited to be at the forefront of this and helping solve some of the key bottlenecks here.
That makes sense, right? And I think this is going to be an overall full stack problem. Clearly, there's no way if models don't get more efficient at this, that they can scale, even with all the technology you're providing. But talking about the technology itself, right? GPU bandwidth is limited. So high bandwidth memory, or HBM, which was geared towards it, is clearly one out of supply for a lot of players. But what more do you need beyond that?
Yeah, see, high bandwidth memory solves a very critical bottleneck in the AI ecosystem, right? Which is how do you provide maximum bandwidth to the compute layer so you could actually respond to queries very quickly, get memory capacity as well supplied to the compute layer. But the reality is that HBM cannot be a cure-all for all the issues that we are seeing in the AI systems space, primarily because of a few bottlenecks. One is the cost. I mean, HBM is very expensive. If you look at the HBM cost, all in, including advanced packaging, CoWoS, and what it takes for testing, and compare that to something like DDR5, there is about a 3 to 4x cost difference between HBM and DDR. Number two is we also have a supply chain problem. We are very increasingly dependent on just one company. TSMC CoWoS talks to about 90% of market share in advanced packaging for HBM, and so we are very increasingly reliant on supply chain bottlenecks and getting HBM to be more broadly adapted. That's number two. And number three is when you think about what it takes for us to go to AGI and ASI. I mean, we are talking about terabytes, exabytes of data that need to be accessed by the AI models. There is no way, from a physics standpoint, that you will be able to stack that much amount of memory right next to your compute die and then package it and deal with the thermal issues that show up with HBM, right? So this is a multi-dimensional problem, and HBM is a good solution, and it's a needed and it's a wonderful solution for for the period that we have just been through, the 2-3 years after ChatGPT. But from here on, as you think about going to AGI and ASI, the complexity of systems that is needed to address the needs ahead of us, it is very risky to just be dependent on HBM. That's number one. Number two is when you think about system cost, the key bottleneck, and we are fundamental believers of this at Kandou AI, is for AI to truly realize its potential, you not only need to cut down costs and increase scale, but you need to do it in a very deployable way where you need not rely on like liquid cooling or more advanced infrastructure. You need an air-cooled system that can do AI models, right? So when you think about what is driving the movement towards HBM, it is the same memory wall bottleneck that we just discussed. However, if you have the right interconnect and the right way to connect memory to the compute die, you can actually achieve a lot using your conventional boards and conventional systems, which could be air cooled, which would really help us with the mission of getting AI to masses. There is no way the common man can afford the cost of infrastructure where it is today and access ChatGPT or access your latest inference algorithms. Like, our goal is to enable the farmer in India to access inference models on his phone. There's no way they'll be able to do it with the cost of infrastructure where it is. HBM and advanced packaging is one part of it, but there are various layers of AI infrastructure which fundamentally need to be redesigned to achieve the mission of democratizing AI.
Yeah, I mean, that makes sense, right? So clearly the democratization has to happen. Clearly solving the memory wall problem is part of it. So let's talk about Kandou's answer to this, right? So the company's core technology was born out of some groundbreaking research conducted by a co-founder and now CTO, Dr. Amin Chakrawi, who was previously a professor at EPFL and whom I've had the privilege of meeting as well to kick off some of the early work we did with you. And the core technology is called Chord signaling, or what you now call copper MIMO. Can you walk us through what that means and what is fundamentally different from conventional SerDes? And was there clearly you've been part of the government task force. You were investing in various startups or companies within the US ecosystem. Was there an aha moment for you that kind of pushed you to thinking this was going to be a really, really big thing?
Yeah, absolutely. So at Kandou, we are a very unique company because we sit at the intersection of information theory and semiconductors. And I fundamentally believe the best innovations in humankind come at the intersection of two orthogonal fields. That has always been the case. If you look at human trajectory, that has always been the case. And we have the advantage of sitting at that unique intersection where based on the work that Amin, my CTO and co-founder, has done over many years, we have really perfected the art of how we can send data efficiently on copper links. And we do that by leveraging certain key principles, which have been proven in the wireless domain, but we have implemented that and proven it at scale in the silicon domain. And fundamentally, it comes down to the physics of how communication links operate. And when you think about the physics, there's only one phenomena that determines the amount of information you can pump through channels, and that is the Shannon limit. And so when you think about today, when you look at a 2-meter 200G copper cable, or let's say 25 like a UCIe channel, you are talking about anywhere between 8 to 20x of untapped capacity that is still remaining in these copper lines. And the reason why this capacity is untapped is because especially at speeds that are required for AI, there is so much of crosstalk and intersignal interference that happens between these copper lines, which is a traditional SerDes designer and everybody in the industry kind of look at it as noise and throw it away. In fact, you spend more energy suppressing this crosstalk and intersignal interference that happens between copper lines that sit next to each other. Now, the reality is that this crosstalk actually has information. It has energy and information about what the bit is on the other line that you can leverage if you knew how to encode the signals before they get on the copper line. And this is where our core innovation and IP shines. Like we have figured out how to encode the signals before they get on these copper lines and implement that in the analog domain in a very power efficient way, such that we leverage this crosstalk and intersignal interference that happens between copper lines to our benefit. And therefore, we're able to design copper links which are higher bandwidth, lower power, and longer reach. That, in the nutshell, is the core IP of the company. And when I came across this technology, see, I was at the US government, and I've working very closely with several stakeholders, including hyperscalers and other parties, to make sure US is at the forefront of AI infrastructure build out. And one of the key bottlenecks that I noticed is the data movement problem within the data center. And if you realize why data centers are so expensive, like 50-60% of your expense goes to your GPU. And if you double click that, about 90% of that expense is HBM and advanced packaging. Your compute die is only 10% of your expense. So fundamentally, within the US government, from a policy standpoint, when we were thinking about how do we democratize AI infrastructure, how do we get more data centers being built in the US without being reliant on power or real estate or some of the other supply chain bottlenecks, it really came down to this, which is how do you efficiently move data in the data center. And so people have looked at optics, people have looked at copper, and so fundamentally what people have overlooked is because you come from a traditional semiconductor background, you don't think of this as an information theory problem. And this is where our IP and our value shine. So when the aha moment was, everybody understands the need to move data efficiently. People are looking at optics and other solutions to solve this data wall problem because they think copper is dead, and they think copper is dead because they are not information theorists. They don't look at these as communication links from a physics standpoint. And so when I came across this, and I was actually at that point even looking at a photonic startup, because I strongly believe this bottleneck needs to be solved, and optics has its promise. But when I came across this fundamental technology, the aha moment for me was, if we can use this fundamental technology to solve some of the key bottlenecks in the AI space, then every single one of our customers would use it because copper has a natural advantage in terms of time to market, scalability, cost, and reliability. It is just that people just didn't know how to fully realize the potential of copper. And so that was the main aha moment. And that's the bet we are taking.
No, so I think this kind of makes me jump to the question I was thinking of. So you've kind of naturally segued to it, right? So clearly Marvell just spent about $3.25 billion acquiring Celestial AI. And again, for photonics communication, right? IR Labs just closed another 500 million round. It's a multi-unicorn co-packaged optics company. And optical interconnect market is supposed to go from just over $3 billion right now to $18 billion in 6 to 7 years. Now, clearly there's directional trajectory this, and obviously photonics does have a future. And I completely understand that your approach is not contrary. It's actually innovating within materials we understand. But can you provide your view on how, Kandou would both coexist and compete with the going trend?
Yeah, absolutely. I think it's very important to realize one thing, which is this is not an optics versus copper game, and this is not a winner take all market. The reality is that for the data centers of the future, you need the best optics technology to work hand in glove with the best copper technology. Because, see, at the end of the day, your CPU and GPU, which are doing the compute, are still electronic. I mean, your bits are still electronic in nature. We don't have a photonic CPU or GPU. So ultimately, you need mechanisms and copper links to get the data out of your compute layer into and feed it to the fiber if you're using a fiber communication channel. So you need the best and the most power efficient copper links to work hand in glove with the optical layer of the future. So industry has this fascination of thinking this is a winner take all, but that's really not the reality. That's number one. Number two is there are layers of the connectivity domain where optics will and should shine. And there are layers of the connectivity domain where copper will shine if you know how to use it. And we strongly believe that if you can unlock the capacity limits that you're seeing in copper today in a very power efficient way, then the domain anywhere between 10 millimeters, which is a die-to-die interconnect, to all the way up to 7 meters, 7 meters, which could cover not only intra-rack, but inter-rack, so 2-3 racks together. If you can solve the data movement problem and the interconnect problem using copper, then the industry would really benefit from that because it has a lot of power advantages, it has cost advantages, scalability advantages, and reliability advantages. So there are natural physics benefits that favor copper in this distance range. Now, when you think about east-west connectivity and when you think about distances longer than 5-7 meters, then optics has a very natural advantage in which we should leverage from both the distance, reach, and power standpoint. And so our bet is that the AI systems of the future will be very bespoke. And you will have nuanced solutions to leverage the physics advantages of whatever material or medium you're using as communication links, depending on what the use case is. So we are focused on the scale-up domain on the PCB board. How do you optimize copper interconnects? And the reality, because going back to the point that I made, which is your bits are fundamentally electronic in nature. Mm-hmm. Right. And so if you are thinking about getting optics into the data center domain, that actually accelerates the need for the most efficient copper interconnects, because if you're able to efficiently get data out of your compute layer and feed it to the optical layer, then it actually accelerates the optics adoption. So we think as fundamentally enablers of high-speed connectivity, whether it's optics or copper, having a strong copper interconnect layer is beneficial no matter where you sit in this equation or in this frontier. And so that's where we are focused on. So in fact, one of the key problems that optics has is reliability and the ability to work at scale. And I've seen this while working in the US government on the supply chain side. When you co-package your PIC with your compute die, there's so much of heat management issue that you need to deal with, right? So, and you do that because co-packaging your optics die with your compute die gives you advantages from a power standpoint. However, if you have a chip-to-chip link, a copper link, which enable you to still get the advantage of co-packaged optics, but not sit on the same compute die, and therefore it expands the design space and you can have a pluggable device with the same benefits as co-packaged optics, then you address the reliability problem that optics has, right? So, and that interconnect that can go across the PCB board would be in copper domain, allowing you to address this reliability problem. And so this is one of the use cases that we are using on our side, and we have customer demand for something like this, where you address some of the key challenges that optics has to accelerate the adoption of optics as well. So I really believe this is a problem that we need to work together, irrespective of which domain you sit in. And I'm very excited about what we could bring to that equation.
And I think you've articulated that case really well, right? Because the general argument that is used for people that don't go to that next level of depth is that, hey, copper may work today and bandwidth requirements are scaling so fast that in a couple of generations, optics is inevitable, right? But really, and this is where I think we agree, is there are horses for courses, and you can do it at a nanometer, a millimeter, a centimeter, a meter, and then kilometers, right? And so we each have a role to play in that. And in fact, Baya has been focusing on the nanometer and millimeter realm, right? Actually on die and across die. So I think the transformation that we're happy to be part of within Kandou AI has been the focus of using that connectivity technology that goes across die into incorporating it with on die kind of much more structure around what you're doing, which I think we focus on, which is how do you make that efficient? How do you actually scale? How do you bring in high radix switching? How do you make the data movement on die as capable as you're doing off die? Do you want to give us a little bit on this transformation that you've had where the digital portion of your company is growing a lot more than traditionally the analog and signaling portion?
Yeah, no, absolutely. And this is where our visions line up, and I'm going to be very excited about the partnership with you. See, you hit the nail on the head, which is fundamentally when you think about what is driving some of the key bottlenecks, it comes down to the scale at which you're implementing systems, right? So traditionally, because of the limitations that we had in copper links, you were limited to a package. And so your chiplet design space was on one package. And so that has inherently limitations on how big your NOC can be and how communications would work between various dies on a single chip, on a single package. What we have done, and you've taped this out in last year, and now we have actually demonstrated it working in silicon, is we have a chip-to-chip link which can go across the PCB board at the same efficiency as a die-to-die link. And so what that does is that it dramatically expands your design space. And so your chiplet space is no longer constrained to the same package. It is actually spread across the PCB board. And so now you're thinking about much larger systems at the scale of which you didn't have before that you now need to manage. But it is all acting as one large MCM. And that is the dramatic, then that has a dramatic impact on the type of systems you design, scalability of these systems, the cost of AI systems. And this is where the partnership that we have with you is really important. And so I strongly believe the whole industry will move towards that direction, where once we unlock the physics and address the physics of these interconnects and how we can make it more efficient, I think the industry will realize that there is a much better way of designing AI systems, which is much more cost efficient and much more scalable. And we at Kandou are also betting on the same, in the sense that we are transforming ourselves to a systems company. We are no longer an IP or a silicon company. We are a systems company. So what we are developing is using our core interconnect technology in AI system space, where we deliver a full stack solution to customers which leverage this unique interconnect technology. And this includes GPU to GPU connectivity, GPU to memory connectivity, networking, and then also optics that we just touched upon. So we are taking an all of the above approach and coming up with systems which leverage this core interconnect technology.
So you're saying this is the natural next step in the transition. I mean, you had discrete elements that were connected by wire 3 decades ago that became discrete elements that connected on copper with a lot more compute in the silicon connecting across die. That became a system on a chip. Then it went to system of chiplets. And of course, CoWoS, et cetera, is taking more about the substrate, et cetera, on silicon. But now you're basically making the PCB a substrate for bigger systems.
Exactly.
Is that a fair analogy?
No, that is a perfect analogy. So we have transformed with our technology the whole PCB into an MCM. So you're no longer on the same package. And fundamentally, Nandan, if you think about computer history and like architectures, right? Like we have come a long way, and there's
Mhm.
every step we take comes with its own challenges, but also opportunities. So if you think about computer architecture in general, today the reason why we are able to have ubiquitous compute is because compute is distributed,
Mhm.
storage is distributed, memory is distributed. Sorry, networking is distributed. The only thing that is not distributed in a very effective way is memory. And
Yes.
this is why and why is it not so why have we struggled as the industry to solve that, is because the way we have been trying to solve it is on the package, and that has a lot of limitations, right? To make distributed memory on the package, you come with it comes with limitations, physics limitations. But now, if you suddenly expand the design space across the PCB board, you can actually have truly distributed memory solution. And then, if your interconnect is even more powerful to go across rack, then you really get the power of distributed memory to help us with the AI implementation. So that's why we are super excited about this. I do believe this is the natural progression that the industry needs to undertake to go where we want to go, and I'm very glad to be a part of it.
No, that's great because in my past history, right, so especially my 16 years at ARM, I kind of saw the transformation for what was system on chip, right? And you could see the transformation from like very tight coupling of the supply chain or true collaboration at process node level, packaging level, IP level, and then system level.
Right.
And I think this is where the industry has to go to succeed. It's a bunch of innovations coming together. So you think about what TC Labs was talking about two podcasts ago, which was 3D memory, which kind of expands your lower cost way to get to it in on the substrate or in package, and then you combine that with more distributed memory on system or on PCB, that starts changing the way you break down the problem or improve the solution to the problem, right? So let me then transition to kind of what's driving a lot of this, right? The infrastructure cost crisis. So you came to Kandou with a very different angle than most semiconductors CEOs, right? Yes, you had electrical background training, but you spent 16 years at Goldman Sachs. You were looking at the government side, Department of Commerce, running investment strategy. Again, it was more, even though I'm sure underlying what drove you there and the success that you came was because of your true tech interest and semiconductor interest. Now, how does having spent that much time in the capital markets change how you look at the problem, right? And can you give us a little bit of a lens on that, and also how that looks at the AI infrastructure cost crisis and how you solve it? I think you've given us plenty of tidbits already, but I'm looking at the overall thesis now.
Yeah, no, absolutely. And, I've always been a technologist at heart. And, even at Goldman, I started and scaled multiple businesses for the firm. So entrepreneurship is something that I'm very passionate about. And so this is something that is close to my heart. In terms of how it has influenced my thinking, I think what people don't realize as much, or people do realize but not pay as much credence, is the concept of ROI in AI infrastructure. And fundamentally, when you think about your infrastructure investments, costs do matter, scalability matters, and how you get to the outcome matters, timing matters. So all of these play a big role. And so spending time in the US government, thinking about the supply chain, thinking about the bottlenecks that we have from an infrastructure standpoint, it really, to me, just re-emphasized the importance of coming up with scalable systems and coming up with more cost-effective solutions, and that is what we are doing at Kandou. In terms of the journey and what has taken me to the stage. My undergrad actually was in MIMO and space-time coding, and so spent a lot of time in my undergrad thinking about space-time encoding and how do you maximize capacity out of wireless antennae and wireless systems. And so to actually get a chance to implement that in the copper wireline domain and make a big difference in this field is really exciting to me. And that has resonated by our partners. I mean, the recent financing round that we just closed not only has strong, financial players, but also strong strategics who are excited to be with us in this journey. And I'm very excited to collaborate with them. And I'm very, very happy to be able to bring about system innovations to this domain, which would really, I believe, help us mitigate some of the supply chain constraints we have in this industry with over-reliance on HBM. And so I'm very excited about this.
Cool. So it sounds very much like you've got have looked at the overall structure, overall supply chain, and decided to place your bets on the max return for both the industry and for the company. Would that be fair?
I certainly hope so.
Okay, so that kind of brings me to kind of towards the closure. I mean, we've been going 35 minutes. This would be awesome. I haven't missed a beat. And it's quite interesting. But see, you drove kind of the rebranding of Kandou to Kandou AI. Basically, it's a new company born from the core technology that Kandou built, right? And now you've already talked about your 448 gigabits per second near-term target, right? But there's a beyond, right? Now, hyperscalers are built today by NVIDIA, by other companies using NVIDIA, and many kind of sovereign AI programs. If you were to project 2 to 3 years out, the beyond portion of it, what does the interconnect layer look like for those systems? And you've already given us a flavor of what you think Kandou can do. Sorry for the pun. I'm a dad. How do you see us fitting into the picture?
Yeah. So when we think about this journey, Nandan, to us, getting to 448 is just the starting point. When you look at the existing copper channels, I mean, let's just take the 2-meter cable. There is about 8 to 9 times untapped capacity there. So if in the industry today is at 224, you could do up to 1.6 terabytes on the same channel, and that is a theoretical Shannon limit. Now, we may not be able to get all the way there. If you look at what has happened in the wireless domain, wireless channels have been able to get to like 60-70% of that Shannon limit. And so for us, 448 is just the starting point. I mean, we want to then go to a 6 handle, an 8 handle, and keep pushing beyond. And that is all in existing copper, right? Now, let's also bear in mind the copper channels itself would improve over time. And so there's a lot of optimization to be done over here. And so what we see is from an industry standpoint, I mean, you look at what is happening at the hyperscalers, what is happening at the suppliers to hyperscalers. Everybody is focused on optics and copper at the same time, because nobody knows which one is going to get there first and get there at scale. And like I mentioned and we discussed, you probably need an all of the above approach to solve some of the problems we are looking at. So I'm very excited about the forward. We are expanding and transforming the company into a systems company. So that is a big transformation that's undergoing at the company. We now have a system software team, we have a boards team, we have a very solid firmware team. We recently opened our design headquarters in India and Hyderabad, and we are very rapidly expanding there. And so increasingly AI is a systems game. Like our customers demand system solutions, and so we are meeting the customer where they want us to be. And so that transformation of going into AI systems is a new muscle that we're developing at the company, and we're very excited to actually bring in talent that is very excited about what our technology can deliver to deliver the whole system. And so we're very rapidly scaling on that front. And so this journey around connectivity, 448 and beyond, I believe we're just getting started. We are multiple years, if not a decade away from when we actually hit the true Shannon limit of copper lines, and I'm very excited to be playing a part in bringing out that untapped capacity.
That's awesome. And yeah, congratulations on the Hyderabad office. Seems like it's pretty full already and growing fast. So let me kind of wrap up with one final question, right? So what's your thinking about what the industry gets wrong about the memory wall problem, or an assumption that if you break today would be the right thing, or if we didn't, would look quite naive in 3 to 5 years?
Yeah, see, I think one fundamental assumption that the industry probably doesn't appreciate as much, or probably gets wrong, is that memory wall problem is a single dimensional problem. I think people think this is a monolithic memory wall. I actually think it's a memory maze. AI doesn't have a memory wall problem. It has a memory maze problem. And what I mean by that is, when you think about CPUs are have a unique memory wall, which is more latency dependent. GPUs have their own memory wall, which is more bandwidth driven. And systems that have both CPUs and GPUs working together have a different memory wall, which is both latency, bandwidth, and capacity driven. So this is a multi-dimensional problem and truly a memory maze. And so this is one thing that I feel that 5 years from now, people will look naive for thinking memory wall is a monolithic problem to solve. And there is a reason why you have different kinds of memory as well. DDR5, LPDDR, GDDR, and then HBM. All of these different types of memories have different latency, bandwidth, and capacity fortes. And so what really the industry needs to do is to optimize the frontier of memory across systems. And that is something that requires an all of the above approach, and not just looking at the memory wall problem as a single monolithic problem. So I feel that's something, looking like 5 years from now, people may realize that it was naive to assume there is only one single memory wall.
Fair enough. Firstly, Srujan, I know it's been tough. You've been jet setting around the world, so thanks for taking the time to join us. Secondly, as you are, we are excited to be part of this journey together, which I believe is kind of fundamentally transforming the data movement and memory wall problem. And all I can do right now is wish you the best. And I'm sure we'll have a lot more of these conversations as we go forward. Thanks again.
Thank you, Nandan. Thank you for having me, and all the best.
So that was Srujan Linga, CEO of Kandou AI. If you want to dig deeper, we'll have links in the show notes to their recent funding announcement, the Synopsys blog piece on the copper MIMO technology, and a few technical explainers on what is Chord signaling for those who want to get deep into information theory. So the memory wall debate, which is one of the most consequential technical arguments happening in AI infrastructure right now, and the decisions that are going to affect it will be made in the next 18 to 24 months. So how much of this is copper? How much of this is optical? All layers on the stack. And we'll be all watching Kandou closely. So if you found this useful, share it with someone building or investing in AI infrastructure. And if you yourself are building in this space and want to come on to the Tech Threads show, you know where to find us. See you next time on Tech Threads.
Thank you for listening to Tech Threads, Weaving the Intelligent Future podcast. Join us monthly for insights into the evolving tech landscape and the future of chiplet technology. If you enjoyed today's episode, don't forget to subscribe and share it with your network, and stay tuned for more expert discussions. Let's weave the intelligent future together.